Let us continue chemical equilibrium. In chemical equilibrium, we will discuss how the chemical equilibrium will be obtained. We will take Haber's process. In the Haber's process, we will take nitrogen gas and hydrogen gas. Nitrogen gas and hydrogen gas we will see. Initially, we are taking these two reactants. So concentration of reactants we are taking. We are taking concentration of reactants. Okay. As time passes, reactants react to give product. Reactants react to give product. Okay. So as time passes, what happens? Reactants react to give product in the sense what happens to the concentration of reactants? Concentration of reactants decreases. What happens to the concentration of products? Concentration of products increases. Okay. So as time passes, concentration of reactant goes on decreasing, concentration of product goes on increasing. At a certain time onwards, concentration of reactant remains constant and concentration of product also remains constant. What does it indicate? So initially we took reactants we have took. As time passing, concentration of reactant reduces because reactants react to give product, that's why. Concentration of product rises as time passes because product is producing, therefore concentration of product rising. When a particular time is attained, at a certain time onwards, concentration of reactants remains constant. There is no further decrease. Concentration of product also remains constant. This magnitude and this magnitude need not be same. Okay. This magnitude and this magnitude need not be same. So concentration of reactant remains same. Concentration of product also remains same at a certain time onwards. What is the reason? What is the reason in the sense? Now let us recall saturated solution of sugar solution preparation. In the saturated solution of sugar, it will dissolve sugar crystals. At the same time, equivalent amount of dissolved sugar is precipitating, which indicates the system has attained equilibrium. Like this, all the process in the universe will reach equilibrium at last. Whatever the process, whether it is natural process or artificial process, whatever the process you take, final is what in the sense equilibrium. So equilibrium in the sense rate of forward is equal to rate of backward. Likewise, here also, what is the final in the sense equilibrium is the final. Equilibrium is possible when in the sense rate of forward and rate of backward are equal. That means as time passes, here initially we took reactants we took. As time passing, concentration of reactant reduces in the sense forward reaction takes place continuously. Forward reaction takes place continuously, therefore only concentration of reactant reduces. At the same time, concentration of product increases in the sense backward also taking place. Since concentration of product increases, backward reaction also increases. Then, what is the relation between rate of reaction and concentration? Is there any relation? Is there any relation between rate of reaction and concentration? For that, what is the relation between rate of reaction and concentration? That we will understand it. Then we will continue this. Sir. Now we have to know it. What is the relation between rate of reaction and concentration? Sir. Now we will take a word called active mass. We are taking a word called active mass. Okay. What is active mass? In the sense, the mass of the substance which is active to for involve in chemical reaction. The mass of the substance which is active to involve in chemical reaction is called active mass. So, now, what is the active mass of ideal gas? What is the active mass of ideal gas? That we will see. Active mass of ideal gas is called partial pressure of ideal gas, partial pressure of ideal gas by partial pressure of ideal gas by standard state pressure, standard state pressure, standard state pressure. Okay. So, what is active mass of ideal gas? Active mass of ideal gas means that is equal to partial pressure of ideal gas by standard state pressure. Standard state pressure. This is called partial pressure of, this is called active mass of ideal gas. What is standard state pressure? Standard state pressure is 1 bar. Standard state pressure is 1 bar. What is partial pressure of ideal gas? This gas exerting how much pressure in the mixture, that is called its a partial pressure. This gas exerts what pressure in the mixture, that is called partial pressure. So active mass of ideal gas equal to partial pressure of ideal gas by standard state pressure, that we can say. Next, we'll take a active mass of ion in solution. Ion in solution. Active mass of ion in solution. Okay, that what means? That is what in the sense that is equal to activity coefficient, activity coefficient into molarity of ion, molarity of ion in solution, molarity of ion in solution by standard state molarity, standard state molarity, standard state molarity. Okay, active mass of ion in solution, active mass of ion in solution is equal to activity coefficient into molarity of ion in solution by standard state molarity. This activity coefficient is a constant term. It is a proportionality constant. This activity coefficient is a proportionality constant term. Okay. So active mass of ion in solution is equal to so and so. Activity coefficient into molarity of ion in solution by standard state molarity. Like that we can say. What is standard state molarity? That is equal to 1 molar. Standard state molarity. Standard state molarity is how much? In the sense 1 molar we can say. Sorry. What is this activity coefficient? This activity coefficient is equal to 1 for infinitely diluted solution. Infinitely diluted solution. For infinitely diluted solution, activity coefficient is equal to how much? In the sense 1. Okay. So activity coefficient is equal to 1 for infinitely diluted solution. So, then what is the active mass of pure solid and pure liquid? That we'll see. Active mass of pure solid, active mass of pure solid is equal to how much? In the sense 1. Active mass of pure solid is equal to how much? In the sense 1. Similarly, pure liquid is equal to how much? In the sense 1. Active mass of pure solid and pure liquid is equal to 1. Why active mass of pure solid is equal to 1? What is the reason? Now we will take calcium carbonate is the solid. This we will take 100 gram. 100 gram if we take, that is equal to how much? In the sense 1 mole. This 100 gram of calcium carbonate is having volume. Volume is how much? In the sense x liter. Now we will find molarity. Molarity of calcium carbonate we will find. Molarity of calcium carbonate is equal to number of moles of calcium carbonate in the numerator by volume of calcium carbonate that we have written. This is called molarity. Now suppose if you take 200 gram of calcium carbonate, it will have 2 moles of calcium carbonate. This volume will be 2x liter. It is 100 gram is x liter, in the sense 200 gram will be 2x liter. That's all, isn't it? Sorry. For this, what is the molarity? We'll see. Molarity is equal to number of moles of calcium carbonate, 2 moles, by volume, that is how much, means 2x, 2 get cancelled, therefore 1 by x. 1 by x mole per liter. Now see, 100 gram of calcium carbonate molarity you see, 200 gram of calcium carbonate molarity you see. So whatever the quantity of calcium carbonate, the molarity remains same. Therefore, active mass of pure solid is taken as 1. Okay. So why it is taken as 1, in the sense this active mass, this concentration of pure solid does not depend on its quantity. Whatever the quantity, concentration, molarity remains same. That's why active mass of pure solid is taken as 1. Okay. Here impurity should not be there. So active mass of pure solid is taken as 1. Similarly, pure liquid is taken as 1. Okay. Next, we will see what called law of mass action. We will see law of mass action. Now we will take law of mass action. We will take. Okay. Law of mass action. We will take. We will take one equation. X of A plus Y of B gives M of C plus N of D. Like this equation we will take. Now, this law of mass action says what, in the sense? Rate of reaction or rate of here forward reaction will take. Okay. Rate of forward reaction. Rate of forward reaction is directly proportional to product of active mass of respective reactants. Sir. Here, what is the reactants? For forward reaction, what is the reactants? That we'll see. A is the reactant. So, active mass of A to the power its coefficient. Here, coefficient for A, what is the coefficient? X. That X we have tried it as power. Then, active mass of B to the power Y. Active mass of this B to the power what, in the sense Y. Here, between them, what is the mathematical operation, in the sense multiplication. So rate of forward reaction is directly proportional to active mass of reactant A to the power X. X is the coefficient into active mass of B to the power Y. Y is the coefficient of B. Then this active mass, in the sense what we have discussed, in the sense active mass means active mass is equal to activity coefficient into molarity by standard state molarity. Standard state molarity value is constant 1m, activity coefficient also constant 1 for infinitely diluted solution. Therefore, active mass of ion is equal to molarity of ion in solution. Molarity of ion in solution. So, rate of forward reaction is directly proportional to molarity of A power X, molarity of B power Y. Okay. Then, rate of backward reaction will take. Rate of backward reaction. Rate of backward reaction is directly proportional to active mass of C power M, active mass of D power N. So for backward reaction depend on which active mass? C and D. Why we have written power M here? Here coefficient is M. Here power N because coefficient is N. Then rate of backward reaction is directly proportional to, in the place of active mass we will write concentration, will write concentration of C power M into concentration of D power N. Okay. Concentration of C power M we will write, this we will write concentration of D power N. Okay. So rate of backward reaction is directly proportional to concentration of C power M into concentration of D power N we have written. Okay. So rate of reaction depends on what? Respective concentrations. Rate of reaction depends on respective concentrations. That's what we are getting from this law of mass action. So law of mass action says that Rate of reaction depends on respective concentrations. Now, we will take this equation. Here we have considered this equation. Here we took reactants, nitrogen gas and hydrogen gas. We are taking initially nitrogen and hydrogen. Therefore, we are taking certain concentration of nitrogen, certain concentration of hydrogen. On mixing both and giving necessity condition, what happens means reaction takes place. That means forward reaction takes place. Forward reaction takes place in the sense N2 and H2 disappearing. N2 and H2 disappearing means concentration of reactant, what happens? Reduces, decreases. So as time passes, forward reaction takes place continuously. Therefore, nitrogen molecules continuously disappearing. So concentration of nitrogen goes on decreasing. Hydrogen concentration also goes on decreasing. Therefore, in this generally we can say concentration of reactant decreases, we can say, as forward takes place. Concentration of reactant decreases as time passes. So, next, what happens to the concentration of product in the sense concentration of product goes on increasing. Concentration of product goes on increasing. Then, at a certain time onwards, what happens to the concentration of reactant means remains same, and concentration of product also remains same. This concentration and this concentration need not be equal in magnitude. So, how the concentration of reactants and products will be there as time passes? How the concentration of reactants and concentration of products will be there as time passes, that we got an idea. Okay, so that graph we will draw. How the what does it say, that we'll see. So now we will take a here concentration will take. In this place concentration will take, here we will take time. Time we are taking. For reactants we are drawing the graph for reactants. For reactants, how the concentration will be there means initially concentration of reactants is maximum. As time passes, concentration of reactant decreases. At a certain time onwards, concentration of reactant remains same. Okay, concentration of reactant remains same. So concentration of reactant, what happens means goes on decreasing, then attains a constant value like this. It is what in the sense concentration of reactants. So concentration of reactants is maximum at when in the sense at the initial. Concentration of reactants is maximum at initial. As time passes, what happens to the concentration of reactant? Goes on decreasing and attains constant value. At certain time onwards, it attains constant value. Sir. Next, we will see concentration of product. Initially, we have taken only N2 and H2 we will consider. We will consider initially we took nitrogen and hydrogen only. We have not taken any ammonia. Then what is the concentration of product initially? 0. Concentration of product is initially 0. As time passes, what happens to the concentration of product? Goes on increasing. At a certain time onwards, this time, certain time we said no, that time is same for reactant and product. At which time onwards reactant concentrations remain same, at the same time product concentration also remains same, but concentration of reactant and concentration of product need not be same at this time onwards. Okay, so as time passes, what happens to the concentration of product in the sense that goes on rising, then at certain time onwards it remains constant. It is concentration of product. So how the concentration of product is there, that we got an idea. Concentration of product, how it is there means like this. So initially what is the concentration of product means 0, because we have not taken any product. As time passes, concentration of product goes on increasing, goes on rising, and then attains constant value. So at which time onwards concentration of reactant and concentration of product remains same, in the sense at this time onwards concentration remains same. Okay, concentration remains same. Concentration remains constant. At this time concentration of reactant is how much, in the sense this much. Concentration of reactant is this much. Concentration of product is how much, in the sense concentration of product is this much. Concentration of product is that much. Therefore, at a particular time onwards, concentration of reactant remains same, concentration of product also remains same. These two values, if we compare, this reactant is less than product. Reactant concentration is less than product concentration. So, now we will see why the concentration of reactant remains same at a certain time onwards, and the concentration of product remains same at a certain time onwards. What is the reason? What is the reason? That means such a type of situation is possible if the system attains equilibrium. If the system attains equilibrium, then only such a type of situation will be arised. If the system attains equilibrium, then only such a type of thing will be arised, we can say. Okay. So this concentration of reactant, we said here, concentration of product, we said, this is not scaled graph. Roughly we have drawn this graph, roughly, not scaled graph. So concentration of product remains constant value, in the sense concentration of reactant constant value, in the sense this is possible only if the system attains equilibrium. Why should we say equilibrium word? That means whatever the process in the universe will attain equilibrium at last. Whatever the process you take, whatever the natural process you take, whatever the artificial process you take, that will attain equilibrium at last. So this situation is possible only when the system attains equilibrium. That time only this situation is possible. So system is attained equilibrium. System is attained equilibrium, in the sense this meaning is rate of forward is equal to rate of backward. That means we allowed a forward reaction. We allowed a forward reaction. Why we allowed a forward reaction? We want ammonia, therefore we took N2 and H2 and we prepared ammonia. For that case, we allowed forward reaction. We allowed forward reaction, but automatically what reaction took place? Backward also took place. That's why we got equilibrium. Otherwise, how do we get equilibrium? Equilibrium means what? Rate of forward is equal to rate of backward. Actually, have we allowed backward reaction? No. We allowed forward reaction only. We wanted to prepare ammonia, so that we took N2 and H2 and necessary conditions we provided. We want forward, therefore we are allowing forward. But automatically what also taking place? Backward also taking place. Automatically backward also taking place. That's why equilibrium we are getting. Sir, now how the rate of forward and rate of backward will be there? That we'll see. We came to know that as per law of mass action, we came to know that rate of forward reaction is directly proportional to concentration of reactants. Initially, how the concentration of reactant is there? Maximum. Therefore, how the rate of forward will be there initially? Maximum. As time passes, what happens to the concentration of reactant? Decreases, reduces. Therefore, what happens to the rate of forward? Decreases, lowering. when equilibrium is attained, concentration of reactant, how it is there? Remains same. So how the rate of forward reaction will be there? Remains same. Okay. So that as time passes, what happens means rate of forward goes on decreasing and then attains constant value. Okay. So how the graph will be there for this, that we will see. So now we will see graphically, we will see. Now we will take a rate of reaction, we will take here. A rate of reaction we will take here. Here we will take concentration, we will take. Okay. For a reactant, we are drawing the graph. For reactant, rate of forward reaction. For forward reaction, we are drawing the graph. Rate of forward reaction initially maximum. As time passes, rate of forward reaction goes on decreasing, goes on decreasing. At a certain time onwards, it remains constant. It remains constant, we can say. So we will take here what in the sense time we will take. We will take here time. Time we will take at a certain time onwards. Rate of forward reaction remains constant. We said it is for forward reaction. It is for forward reaction. Okay. So why forward reaction rate is maximum in the beginning? In the initially, rate of forward reaction is maximum. What is the reason? Why rate of forward reaction is maximum in the beginning? Because initially we took reactants, we took initially we took reactants. Therefore rate of forward reaction is maximum initially. As time passes, why rate of forward reaction decreases? Because concentration of reactant decreases. At equilibrium, once equilibrium is attained, the rate of forward reaction remains constant. Why is it so? Because concentration of reactant remains constant. That's why. Okay. So how the rate of forward reaction is there, that we got idea. Next we will go for rate of backward reaction. Initially, we have not taken any product. So concentration of product is 0. Therefore, rate of backward reaction also 0. Rate of backward reaction depends on concentration of product. Since concentration of product initially is 0, rate of backward reaction also 0. As time passes, what happened to the concentration of product? Increases, rising. Therefore, what happens to the rate of backward reaction? That also increases, rising till attains equilibrium. Once equilibrium is attained, how the concentration of product is there? Remains constant, remains same. Therefore, how the rate of backward reaction will be there? Remains same. Then equilibrium means what is the condition? Rate of forward reaction is equal to rate of backward reaction. That is the condition. Rate of forward reaction is equal to what? Rate of backward reaction. That is equilibrium. Okay. So now for backward rate of reaction, we will draw with the time. So rate of backward reaction initially is 0. As time passes, the rate of backward reaction goes on increasing. Then at certain time onwards, it remains constant. That means constant in the sense become equal to forward. So this is what in the sense backward rate. Okay. Rate of backward reaction goes on increasing at a certain time onwards, remains constant. That means being equal to rate of forward reaction. So rate of forward reaction and rate of backward reaction will be equal at certain time onwards. At which time in the sense at equilibrium time. So at this time onwards, rate of forward is equal to rate of backward. Rate of forward is equal to rate of backward. Therefore, this time is called what in the sense? Equilibrium attained time. So this time onwards, the system is in equilibrium only. Why do we say equilibrium is called dynamic? Why don't you say static? Because even after attaining equilibrium, forward reaction takes place continuously. Backward reaction also takes place continuously with equal rates. Otherwise, this graph would have touched the x-axis. Is this graph touching x-axis, time axis? No, it is parallel to time axis. That means forward reaction takes place continuously even after a system attained equilibrium. Backward reaction also takes place continuously even after system attained equilibrium. How the rate of forward and rate of backward is there? Being equal. Okay, therefore equilibrium is called dynamic equilibrium. Okay, sir. So for rate of reaction and time we have drawn the graph, and concentration time we have drawn the graph. Sir, we said one point. Once the system is attained equilibrium, rate of forward and rate of backward remain equal. Sir, this forward reaction rate, backward reaction rate remains constant, equal. But concentration of reactant and concentration of product at equilibrium is not same. See that here concentration time. Concentration of reactant remains constant, this value. Concentration of product remains constant, this value. This graph is not scaled, roughly drawn. Concentration of product remains constant. Sorry. Concentration of reactant and concentration of product remains constant, but different values, different magnitudes, in the sense how rate of forward and rate of backward will be equal. Rate of forward depends on concentration of reactant. Rate of backward depends on concentration of product. When the rates are equal, why not concentrations? We are saying concentration of reactant and concentration of product at equilibrium need not be same, we said. But we are saying rate of forward is equal to rate of backward. When concentrations are not equal, when concentration of reactant and concentration of product at equilibrium, when they are not equal, how do we say rate of forward is equal to rate of backward? How do we say? For that, now rate of forward reaction, now we will see. Rate of forward reaction is directly proportional to concentration of reactant power some x. Then rate of backward reaction is directly proportional to concentration of product power y. Now year power need not be same, that depends on experiment. This power x and power y is from experimental result. It need not be same. Okay. And here proportionality constant, how it will be there? May be same or may not be same. Therefore, rate of reaction not only depending on concentration but also power and proportionality constant. It is also depending on power. Therefore, we can say that at equilibrium, concentration of reactant and concentration of product need not be same. We can't say whether they are equal or not. We cannot say. They need not be same also, we can say. But at equilibrium, rate of forward and rate of backward must be equal. But concentrations need not be equal. Okay. Therefore, at equilibrium, understand it, at equilibrium, concentration of reactant and concentration of product equal, we should not say. We should not consider equal. We have to say we do not know. We have to see the experiment, then only we have to say. But we can say at equilibrium, rate of forward and rate of backward equal, we can say. Without seeing the experiment, we can say. Without seeing the values, we can say. Have we got idea? Sir. So at equilibrium means concentration of reactant remains constant, concentration of product also remains constant, but these two magnitudes need not be same. Okay. But at equilibrium, rate of forward and rate of backward must be equal. Okay. Sir. So what is equilibrium that we got? Now we will continue. Law of mass action will continue. So what law of mass action says, that we will see. Okay. So we are going for law of mass action. Okay. So as per law of mass action, we have written certain points, that those points we will say now. As per law of mass action, rate of forward reaction is directly proportional to product of active mass of reactants A and B to the power respective coefficients. Here for A, what is the power means x, for B, what is the power means y. Okay, it is the rate of forward reaction. Next, this rate of forward reaction we can say as rate of forward reaction is equal to proportionality constant for forward reaction into active mass of A power X, active mass of B power Y. It is for rate of forward reaction. Okay. Next we will see rate of backward reaction. We will see. Next we are going for rate of backward reaction. Now rate of backward reaction is equal to proportionality constant for backward reaction into active mass of C power M, active mass of D power N. Okay. So we have written like this. So now we will go to condition equilibrium condition. At equilibrium, now we are going for equilibrium. At equilibrium, okay, rate of forward is equal to rate of backward. At equilibrium, rate of forward is equal to rate of backward. Let us substitute this rate of forward. We will substitute, that is Kf into active mass of A power X, active mass of B power Y is equal to rate of backward. We will substitute, that is equal to Kb into active mass of C power M, active mass of D power N. Then we will rearrange this one. That is Kf by Kb. Kf by Kb is equal to what in the sense? Active mass of C power M, active mass of D power N by active mass of A power X, active mass of B power Y. Okay. This Kf by Kb is called what in the sense? Equilibrium constant. Equilibrium constant. This Kf by Kb is called what in the sense? Equilibrium constant, we can say. Okay. So equilibrium constant K is equal to Kf by Kb, which is equal to active mass of C power M into active mass of D power N by active mass of A power X, active mass of B power Y. Okay. Now, equilibrium constant, we got it. This you understand it in this, for this one, right side is what is there? C and D is there, that you have to write in the numerator. What is there in the right side of the given equation, that you write in the numerator for equilibrium constant. For getting equilibrium constant, what you have to write in the right side, what you have to write in the numerator, in the sense what is given in the right side of equation, that you have to write in the numerator, denominator. Denominator, what you have to write means in the equation what is there in the left side, that you write in the denominator. Okay, in the left side what is there? A and B. Therefore A and B we have written in the denominator. And for A, what is the coefficient, that you write power for active mass of A. So active mass of A power is X. For B, what is the coefficient in the equation? Y. That you write active mass of B power. Okay. For B, what is the coefficient? Y. That you write power for active mass of B. In the same way, active mass of C power is M. Active mass of D is D power is N. Okay. This is called equilibrium constant. Okay. So next we will see. Now we will see equilibrium constant in terms of concentration. We'll see. Then we'll see equilibrium constant in terms of pressure. We'll see. Then we'll see equilibrium constant in terms of mole fraction. We'll see. Like this, we can say in any manner we can say. Okay. Now we are taking equilibrium constant in terms of concentration. Concentration means molarity. Okay. That is equal to what we have to write in the numerator? Right side of equation. So in the numerator, you write right side of equation. Right side, what is there? C is there and D is there. Okay. C is called what? This bracket is called what? This square bracket means what? This bracket says that equilibrium concentration of C. This indicates that equilibrium concentration of D. Then for this, you have to write power. What power you have to write means in the balanced equation for C, what is the coefficient, that you write it as a power. For D, what is the coefficient in the balanced equation, that you write it as a power for D. Then denominator, what we have to write. In the given equation, left side what is there, you see. Left side what is there? A and B is there. That you write equilibrium concentration of A